This section we're going to model after the previous section, which was vectors in R2. We're going to talk about n vectors, vectors in Rn. Let's make some definitions first. Let's talk about vector addition in Rn. First, what is a vector in Rn? Let U be one such vector. Instead of having 2 numbers or 3 numbers, it has n numbers. N is some positive integer, like 17. Be U1, U2, up to U17 or UN. A vector in R5 would be something like 1, 0, 2, negative 4, 11. That vector is in R5 because it has 1, 2, 3, 4, 5 values. And V is also in Rn. It has n components. Let these 2 vectors, let U and V be 2 vectors in Rn. Let's talk about how to add them. The sum of U and V, which we denote naturally enough as U plus V, is U plus V equals, and we add component by component. We do U1 plus V1, that's the first component. U2 plus V2, that's the second component of the sum. And then all the way down to we add the last components, Un plus Vn. That's U plus V. U minus V, all these pluses would just be minus. Of course, if you can, actually do arithmetic. I'll show you what I mean by that. If you wanted to add these 2 vectors, 1, 3, negative 2, negative 7, and say pi. You want to add that vector in R5 to another vector in R5. Negative 4, 3, 4, 2, and 17. Well, you add the first values because it says add. 1 plus negative 4, negative 3. 3 plus 3, 6. Negative 2 plus 4, 2. Negative 7 plus 2, negative 5. Now, in these 4 additions we did, we actually had to do some calculations. We actually had to know what 1 plus negative 4 was, what's 3 plus 3 is. None of them are hard, fair enough. But here's a much easier one. Nonetheless, students let this calculation bother them a lot. What is pi plus 17? Very simple. It's pi plus 17. Normally, if somebody asks you what 2 plus 3 is, and you said, oh, I know that one, it's 2 plus 3. You wouldn't get, you get strange looks on an exam if the teacher says 2 plus 3 equals, and you wrote 2 plus 3, I would put a check there saying it's equal, but I wouldn't give you any credit. The nice thing is somebody asks you what pi plus 4 is, what does it equal? You're allowed to say it's pi plus 4. It's easier. Don't let pi and e and numbers like that bother you. The square root of 7 plus 2 is the square root of 7 plus 2. So vector addition is nothing major. If instead of addition it said subtraction, well then these answers are wrong. We have 1 minus a negative 4. We have 3 minus 3. negative 2 minus 4, negative 7 minus 2, and pi minus 17. We would have that answer if it were subtraction. Vector u minus vector v, where vector u is what it says below, and vector v is what it says below vector v. Now, the next thing we should talk about, after talking about how to add two vectors and how to subtract two vectors, we should talk about scalar multiplication. And rather than giving a formal definition like I planned, since it models so well after scalar multiplication of a matrix and scalar multiplication in R2, we'll just do one. If u was 7, 3, 2, 4, and you want to multiply it by 5. In grammar school, you would have seen this problem here as follows. 5 times 7, work that out. What is 5 times 3? That is, you'd have to compute some multiples of 5. Answers are 35 and 15 and 10 and 20. And that's what this is. Because 5 times 7 is 35 and 5 times 3 is 15. You multiply each number in the vector by the scalar, 5. 5 times 4 is 20. Don't think of it as any different than when your grammar school teacher asks you to do 4 multiplication problems. It's just short notation. What does this problem mean? What does this in this enclosure mean? It means do these 4 problems. That's all it means. Nothing more, nothing less. And you have to put the answers 35, 15, 10, and 20 in the correct places. 7 was first, so you put the answer to 5 times 7 first. 3 was next. 5 times 3 is 15. 5 times 2 is 10. 5 times that 4 is 20. It's just being asked to do a handful of multiplications, and that's it. Let's talk about this theorem. Let u, vector v, and vector w be vectors in Rn, and c and d are scalars. C and D are scalars. Then the following properties or facts are as follows. Call the first one alpha. It says that, remember, U, V, and W are in Rn. It says that if you add two vectors in Rn, you get back something in Rn. This is for all U and V in Rn. This is called the closure property. Closure under plus, or circle plus if you prefer. The next one is A. It says that if you add vector U and V, or if you add V to U, it's the same as adding U to V. Associative law, the commutative law. The order you add the vectors in, it's up to you. The next property says you have three vectors that you're adding, u, v, and w. Same three, same order, u, v, and w. There's two different ways of doing it. You can add the first two together, and whatever answer you get after you add these together, add w to it. Or you can add the last two first, and then you take u and you add to it whatever you got for v plus w. Now, when might you want to add it in opposite order? Well, if you have 3, 4, 5, that's vector u, and you want to add 7, 8, 9 plus negative 7, negative 8, negative 9. I would prefer to add the last two first because they add up to 0. Okay. 3, 4, 5. This first vector plus the answer to that, which is the 0 vector. Well, that's easy. That's just 3, 4, 5. Now, of course, if you wanted to, you could have added those two vectors first. 3 plus 7, 4 plus 8, 5 plus 9. And then you add on the last vector, negative 7, negative 8, negative 4. 10 plus negative 7 is 3. 12 plus negative 8 is 4. 14 plus negative 9 is 5. This was painful. In my opinion, this was painful. It's a lot easier to add these two vectors and get the 0 vector. Or even if you almost got the 0 vector. Maybe this was negative 8. So you just got 1. So in the first two cases, you're just adding 0, which is easy to do. And in the last case, you're just adding 1. I would rather do that problem. But let's just go back to the original one. If you combine A and B together, kind of says you can add any two first you want. You can even add the first and the third. Now, if you don't see that, you need to. You need to. Why are you allowed to add the first and the third? And let's suppose you are given this problem, just the way it is right now. The parentheses say to add the second two first. And you don't have to. You could apply the associative law because you're like this now, and you could invoke the associative law and put it this way. But what I'm going to do is I'm going to use rule number A first. I'm going to say 3, 4, 5 plus, and I can switch these two. U plus V is V plus U. Then I get negative 7, negative 8, negative 9 plus 7, 8, 9. Now I can invoke the associative law. I can say, you know what? I'm going to keep the order of the three vectors the same. Not going to change that. But you know what? Instead of putting the brackets around the second and the third, I can put it around the first and the second. Now notice, if I call this vector 1 and this vector 2 and this vector 3, well, this here is vector 1, and the next vector is vector 3. That is here, I'm adding 1 and 3 together. The associative law and the commutative law says any order you feel like. So your job is to know that, to know the associative law and the commutative law and the consequences of having those two properties. Letter C talks about the zero vector. There exists a zero vector in Rn such that the zero vector plus the vector u, which according to letter A is the same as vector u plus the zero vector, gives you back u. And this is for all u in Rn. It is any vector in Rn. Any vector in Rn. If you add the zero vector to it, or you add any vector to the zero vector, or you add the zero to the any vector, you get back that vector. That's pretty neat. Letter D goes on to say, for all u in Rn, there exists a negative u in Rn such that the sum is the zero vector. There's always an additive inverse. These all dealt with addition of vectors. Always addition, addition, addition. Always addition, and more importantly, only addition. Only operation was addition. Well, there's another operation. It's called scalar multiplication. If you have a vector u, and you multiply it by c, and u is in Rn, the result is in Rn. Okay, which makes complete sense. I mean, if you take 7, 3, 9, which is in R3, and you multiply each number by 11, it's insane to think that you're not going to get back 3 answers. Multiply 3 numbers by 11. Somebody asked you, what do you get when you multiply these 3 numbers by 11? Are you only going to give them one answer? Okay, I mean, the answer is maybe you would. I mean, somebody says, what do you get when you multiply these 3 numbers? Has 3 in my mind. What do you get when you multiply those 3 numbers by 11? It's not unreasonable for you to say 88. The bottom line is, you understand what I mean. They should tell you 88 3 times. Okay, so this vector is in R3, and when you multiply each element by 11, you're going to get something in R3. 7 through 9 is in R3. You scale it by 11, you get something back in R3. That's not going to change. And that's a reasonable assumption. And maybe I shouldn't call it an assumption because it can be proved to be true. That's why it's part of the theorem. Okay, now since we did something to a vector in U, we scaled it by C, and we got something back in the same space we started with. U was in Rn. We call this closure. Closure under the operation was scalar multiplication. Now we have some properties that involve scalar multiplication and also addition, but they will have scalar multiplication. Letter E goes on to say, if you have the sum of 2 vectors, so they're the sum, but you want to scale that sum. You want to scale the sum of U plus V. Well, it says you can scale U, you can scale V by C, and add them up. Letter F goes on to say, if you have a sum of scalars, I'm going to multiply that by the vector U. Then the line above, you have the distributive property. Same with the bottom line. You can take U and scale it by C, and then plus or minus. You can then take V and scale it by U. There's 2 more. I'll put them on the right here. Letter G says if you scale u by d, and then you scale that new vector by c, an alternative is to multiply c and d together, multiply that by u. And there's definitely reasons you want to do that. If you had, I don't know, 2/3 times 6/2 times a vector u. Well, of course, okay, 6/2 is 3. Okay, so suppose you have, I don't know, 9/2. It's so much easier to do 2/3. So first, to do it the way we have it here, you'd have to multiply every entry by u by 9/2. And then whatever you get, you have to then multiply every entry by 2/3. If you do the multiplication first of the scalars, you just get 3. So every entry gets multiplied by 3. Or worse yet, or a better example where you really want to do this is, what if you had a 3/2 u, and you're going to multiply that result by 2/3. The thing is 2/3 times 3/2 is 1. 2/3 times 3/2 is 1. So rather than, well, let me write this bigger. So if you wanted to compute 3/2u, you'd have to multiply every entry in u by 3/2. And then whatever you get after you do that, you then have to multiply everything by 2/3. But if you did the multiplication of the scalars first, that multiplication is just 1. 1 times u is just u. So all you had to do was 2 multiplications. And even if you don't know what 2 times 3 is, you should know it's the same as 3 times 2. And of course you know what 3 times 2 is. But if the numbers were less friendly, like 78 times 22, but you're dividing it by 78 times 22. Well, that's clearly going to be 1. The next and last statement in this theorem, a rather easy one, it says that for any vector u in Rn, if you multiply it by the scalar 1, get back u. And of course that is right. And if you take 1 and you multiply it by u1, u2, up to un, well, when you multiply 1 by 1, 1 times u1 is u1, 1 times u2 is u2, 1 times un is un. So 1 times u is just the vector I'm putting the brackets around, but that's u. In fact, there's the proof for letter H. Nothing magical there. You need to know these properties. But more importantly, you need to use them when need be. There's one thing somebody asks you is, if u and v are vectors, is u plus v equal to v plus u? And you may think for a second and naturally picture what's going on in your head and say, yeah, of course that's true. But if you don't know it cold, you won't use it when it's beneficial to you. Now, in R2, that is in the xy plane, if you have vector u and you have, say, vector v, which is longer, if you go to the to the head of vector v, that is, you go here, and you go parallel to u. You go like that, even further if need be. In fact, I think we need b. Let's make u a little bit shorter. Now, you do the same thing at vector u. You go to the head of u, but now you go parallel to v. You go parallel to v. And you meet out there. You meet out at this point up here. Well, this vector from the origin to where those 2 points meet, that's called u plus v. Now, let me just make one other comment, please. This figure is a parallelogram. It's a parallelogram. And you may say, well, why are you talking about R2? We're not in R2. We're in R3 and R4 and R5. Well, the next statement is just for R3. The same exact parallelogram that we just had in R2 occurs in R3. Imagine, imagine you have a compass. And in particular, let's look at the 2 legs. You could ignore this handle on top. That's pretty wide. We could have the opening be less wide. But I didn't mean to make it shorter. Or we can have the opening be really wide. Okay? Now let's further assume one other thing. That these 2 legs or vectors, they don't have to be the same length. Okay? They don't have to be the same length. Okay, now, with respect to your compass, ignore that piece up there. If you were to take your compass, and again, you know how some compasses, you get to attach a pencil? Or make the pencil long. That way, this one is not as long as that leg. They don't have to be the same length. And so let's just stress on the one that remains. If you were to hold that compass, and you have a little handle to hold it, if you were to hold that compass in the middle of the air, just right in the middle of your work area right now, just take your compass and hold it up. If you were to take a sheet of paper, and you made sure that the sheet of paper touched both of these arms, or let's call them vectors. Okay, let's even call this point there the origin. Well, we're not in R2, so let's not go there. Now, the bottom line is, you can make a plane by putting a sheet of paper that contains those 2 arms or vectors. Okay, and that piece of paper is flat. In fact, let's just make it a little bit longer looking. But nonetheless, it's lying flat. The compass is lying flat on this piece of paper. Well, then, it's just like R2. It's just your plane is not on your desk anymore, because normally you write your XY axes on your tabletop. You don't usually hold this piece of paper up in space, but you could. And then, if this is vector u and this is vector v, you could draw your... oops, that was a terrible picture. At this point, at the head of u, I want to draw a line that's parallel to v. And at the head of v, I want to draw a line that's parallel to u. I want to see where those two lines intersect. And it looks to me like right there. So whether you erase this or not, it really wasn't needed. Well, there's your parallelogram, and the vector u plus v goes from the origin right to the point of intersection. So even in R3 it works. The sum of the vectors tend to form this parallelogram. That's because R3 can be pictured in 2 dimensions. Suppose we have 2 vectors in R3. Let P equal the vector x1, y1, z1, and vector Q is equal to x2, y2, z2. And we want to find the vector from P to Q. Notice the arrow's pointing towards Q. P to Q. And the way you find that vector is you do Q minus P. You do that for the x component. You do y2 minus y1 for the second component. And then lastly, you do z2 minus z1 for the third component. I'm going to work out 1 or 2 examples, and then I want to make a very strong comment or appeal. If you have P is equal to 4, 1, 7, and Q is equal to 3, 1, 2, and say you want to go from Q to P, Q to P. So you do P minus Q. You do 4 minus 3, 1. You do 1 minus 1, 0. You do 7 minus 2 is 5. And you say that wasn't bad. If you wanted to do P to Q, Q is going to Q. The arrow is above Q. I've never really seen it written this way, but it's going from P to Q. You start here and go in the direction of the arrow to Q. Either way, you go into Q. So you do the Q minus the P. 3, take away 4, negative 1. 1 minus 1 is 0. 2 minus 7, negative 5. And since you did the subtraction backwards, it's not a surprise that these differ by a minus sign. So it's very, very simple to find the vector from P to Q. Now, I have students coming up to me all the time. And they go, Professor, I did every problem in the book, and I still failed your test. I studied very, very hard. I'm not suggesting the students are not being honest. Maybe, in fact, they studied even more than they admitted to studying. They're embarrassed they studied so much and they did so poorly. They'll say to me they went blank during the test. I knew everything going into the test, but then I blanked out. I suspect there are some students who really, really do blank out. But I have a strong suspicion that the majority of students do not blank out. They thought they knew the material. That's why they think they blanked out. Now, if you were said to look at this problem again, find the vector from P to Q. Now, they just got so much into a habit of doing Q minus P. 3 minus 4, 1 minus 1, 2 minus 7, and then they did the next problem. It said P is 1, 1, 1, Q is 3, 2, 4, and find the vector from P to Q. Oh, Q was second. They did 3 minus 1, 2 minus 1, 4 minus 1, and they did 100 of these. And then on the test, they got it wrong. And the reason, in my opinion, that they got the problem wrong is they didn't study the most important thing. And before I tell you the most important thing, you're in linear algebra, you should know how to subtract. You shouldn't be doing 100 subtraction problems, or even 3. Just make sure you're getting it right and then stop. What you should study is that if you have P to Q, you should say to myself, I have to find the vector P to Q where the arrow is above the Q. I'm going to do the Q's minus the P's. Now, if you studied that, and then you couldn't remember it on the test, then I'll admit you went blank. Then I'm like, well, if you knew before you came into the test that when it says P to Q or A to B, or the arrows are above the B, and you knew to do the B points minus the A's, take the X values of B, take away the X value of the A. Take the Y value of B, take away the Y value of A. In R3, continue on. Take the Z value of B and take away the Z value of A. If you knew that, but before the test, 5 minutes before the test, you knew that, and then you got it wrong on the test because you left it blank, then absolutely you went blank. But until you can tell me at some point you studied that when it says, U to V, with the arrow over V, that you do V minus the U's, then I don't believe you went blank. You need to study the steps. Stop doing only problems in your studying. Okay, so assuming you know how to subtract, just a waste of time doing 10, 20 problems of subtraction. You need to be able to say what the steps are. And that can really minimize your study time. Rather than doing 15 subtraction problems, you just do 1 or 2 and say, yeah, the steps are obvious. I just have to remember the steps. From P to Q, you subtract P to Q, you do Q minus P. Okay, now, you really should also understand why it's that. Now, let's look at the case in R2. Suppose you have the vector P, and it is x1, y1. x1, y1. And you have the vector Q, which is x2, y2. And you want the vector from P to Q. You want that vector. You have to remember that if you have this vector, I don't want to use the same letters, call it A, and the other vector starts right at the tail of A, the vector B has its tail at the head of A, and it goes to this point here. Well then, this vector call this vector C. Well then, A plus B is the same as C. Those 3 vectors have to add up. That is, this vector P plus whatever we call this vector must notice that the tail of this unknown vector is right at the header P, and it ends right there. P plus this unknown vector ends up right here. It ends up right there. But that's exactly where Q ends up. So it's the same as Q. Well, what do you add to P to get Q? you need to think 0. Because you should know how to get to 0. Just take away p. And now that you're at 0, you should know how to get q. Just add q. This unknown vector is q minus p. And that is the vector we're looking for. And if you don't believe this is true, p plus q minus p, well, p minus p cancels, and you get q. If you hated the way I did it, by thinking, call it x, and then solve for x by taking away p from both sides. If you have vector p and you add q minus p, you will get q. Okay. Let me just erase this a little bit and then finish up by showing you that p to q is exactly what we want. So again, p to q is this vector right here. It's the vector that literally goes from p to q. Went from p to q. And we said it's q minus p. It's q minus p. So from p to q, you just do q minus p. For q is x2, y2 minus, and p is x1, y1. You subtract the first components, you get x2 minus x1. You subtract the y components, you get y2 minus y1. That is what PQ is. And if you, okay, that's right. That's right. Now, if it was in 3 dimensions, then you had Z2 and comma Z1, well then, it's gonna be the same. Of course, I just hand waved a little bit, or a lot. Z2 minus Z1. So at least in Z2, R2, I convinced you that it works. And it works in R3 as well. And even further, R4, R5. Okay. So, letters talk. So now, even if you quote go blank on the test, you should be able to handle what I did. I'll show you again. You say, look, I got the formula. But here is P, and here is Q, and if I went this way, call this X for a moment. Well then, first I went to Q, here's the head, and then I went to X, then I added X, and what I got was P. That's true. So our X is P minus Q. And X goes from Q to P. Goes from Q to P. So to find out Q to P, oh yeah, I remember now. If the arrow's above the P, my teacher said do P minus Q. Okay. If it were the other way, if you wanted to know from Q to P, if this is P and this is Q, and you want to go from P to Q, well, call this X. Well then, vector P, it ends here, and this vector takes on over. So you add X, and you say, well, why can't you add Q? Because Q ends here. It doesn't start here and goes to the origin. It doesn't have the head at the arrowhead at the origin. It has it at Q. Well, P plus X is the same as going from the origin to Q, which is just Q. Bring the P over, we get x is q minus p, and x is, well, it goes from p to q. Oh, p to q. Oh, yeah. If the arrow's above the q, you do q minus p. I remember my teacher saying that. Okay. I can forget this anytime I want, and with a very, very simple diagram, I can remember, oh, P to Q, we do the Q points minus the P points. You need to be tough and have some ways of backing up. You can't backing up what you don't know. There's lots of things I don't know, or I don't remember, but I can quickly get them back. Could very, very quickly get it back. Like, for example, it's embarrassing how I never, ever remember the sides, where the sides of a 30, 60, 90 right triangle go. But I do know the numbers are very similar to 1, 2, 3. And it's square root of 3. 1, 2 square root of 3. This is the largest number, and 90 degrees is the largest angle. Opposite the largest angle goes the largest side. Okay? And this is more than 1. Take numbers less than, if this equals k, well then k times itself should give you 3. You can't take numbers less than 1, multiply it by itself, and get more than 1. So we know this is more than 1, and that is 1. So that's 1 is the smallest, and angle 30 is the smallest, and the middle size is the 60 and the square root of 30. That is, you have 30, 60, 90. I'm putting them in increasing order, and 1, 2 square root of 3. 1 is the smallest, square root of 3 is the next, and 2 is the largest. So now I know how to do a 30, 60, 90 triangle. 60, 30. Opposite 30 is 1. Opposite 60 is square root of 3. Opposite the 90-degree angle is the side that's 2. And I always get it that way. I hardly ever remember it. And I can go a whole semester teaching a trig class and never remember that even once. But I don't have to. I don't mess up in class because I just picture what I just drew, what I just drew and said. Whether I physically write it on the board or not, I could at least picture it and go, oh yeah, opposite the 30, it must be the 1. Okay, let's talk about the length of a vector. First, a minor comment or a major comment. There are 3 terms for the length of a vector. One is the length, one is their magnitude, or magnitude, or the norm of a vector u, which is u1 through un. What is their length, or the magnitude, or the norm of the vector u? And the answer is, it is, you take each component, u1, u2, all the way up to un, and you square them, and you add them up. And then you take the square root. Now, again, that's what you need to be able to say to yourself. Not just do 15 problems. Okay? It's reasonable to assume that you know how to square numbers, you know how to add the numbers. So doing 19 problems is not the greatest idea. I do want to just throw in some notation. Yes, that is their length, but we have a symbol for it as well. And it's u with 2 bars. That's how we denote the length or the magnitude of a vector u. So for example, if u is 3, 1, 2, then the length of u is, well, you square the 3, you square the 1, you square the 2, you add them up, put a square root sign over it. If you can say that, you should have it correct on the test. Then, if you say, well, you know what, I did study that, exactly what you suggested, and I forgot it on the test. And I'm like, yep, you went blank. But if you never said to yourself, to find the length of u, you square each of those values, and you add them up, and you put this strange symbol above it, I'll say you didn't have it. That's why you got it wrong. You never had it. If v is 3, 0, 4, and the length of v is going to be 5. Plus 3 squared is 9, plus 0 squared is 0. Sum is 0. Sorry, sum is 9 so far. 4 squared is 16. 9 plus 16 is 25. 9 plus 0 plus 16, square root. The square root of 25, which is good old 5. The length of this vector is 5. So, for the whole course, don't memorize. Okay, try to, I don't mean don't memorize. Know how to state the steps in doing a problem. If you can state the steps and even understand why the steps are what they are, you have a good chance of remembering it for the test. And the next thing we're going to talk about is the dot product. Now, we spoke about dot products before. It's nothing new. If u is u1, u2 up to un, and v is also an Rn, v1, v2 up to vn, well then u dot v is, you multiply the first components together, plus you multiply the second components together, plus, etc. And then eventually you multiply the last components together. To actually do this is probably easier, simpler, faster to write the vectors vertically. For example, if u is 7, 1, 2, 3, I want to dot it with vector v, which is 2, 1, 4, 5. It's very simple to see what we're multiplying. Multiply the first values, and you multiply the second values, you multiply the third values, and then the last values. This is 15 plus another 15 is 30, plus 8 is 38. Now, of course, you can absolutely have done it horizontally. It just takes a little bit more time to see, I have to go, seriously, no lie, I have to go way over here to see what to multiply the 2 by. But here, it was right there. By the time I looked over, I could have written down the answer. Now I write down the answer. And again, I have to look over the same distance all the way over here. When here, I just had to look across the shorter distance. That's all I'm saying when I say it's faster. And also, it's going to be much harder. Let me just clean this. Let's write it down again. No, I'm not. It's going to be much harder to say accidentally multiply this 3 with that 4. Multiply the 2 with the 4 and the 3 by a 4. Doesn't mean you don't know what you're doing. Made a careless mistake. But now, when you go to this 3, especially Okay, when you go to this 3, you have to remember to go to the 5, not the 4. Okay? Maybe what I should have said was the following. It's easy. It's kind of hard to do the 2 to the 5. But over here, you really want to go 2 to the 4, but you might go off by 1. I mean, the numbers are far apart. Here, they're literally they are lined up. They are lined up. If you insist, now that I mentioned the word line up, what comes to me is if your teacher says, you know what, you have to write them horizontally. Well, make the teacher happy, but also make yourself happy. And this step, you don't have to write down extra to write both vectors vertically. That is, if you have 3, 1, 2, 1, I need to dot it with 4, 1, 2, 5. Just put the 4, 1, 2, 5 underneath, and then go 12 plus 1 plus 4 plus 5. I don't know, looks like 22 to me, and then erase this, and the teacher will not know that you did anything tricky. Now what I meant was, here I just wrote one vector extra. I had to write the 2 vectors I'm dotting. Now, if you went and wrote them vertically, now I'm writing 2 vectors. Again, 12 plus 1 plus 4 plus 5. Okay? Whatever you do, it's probably best to have them lined up. It's probably best to have them side by side. One beneath the other. That's just my opinion. If you're running short of time and you're rushing, you won't, using the horizontal method, you might multiply the second entry by the third entry. God forbid it's in R7. You might multiply the 5th one by the 4th, or the 5th, or the 6th, just because you're in a rush. And if you multiply by the 5th, you'll be right, as long as you didn't make other mistakes. So, I think it's important that you understood how writing them side by side will eliminate some silly mistakes. That's the difference between an 89 and a 91. That is the difference between an A and a B, maybe. Theorem. If U, V, and W are vectors in Rn, and C is a scalar, some real number, then the following facts are true. If you dot U with itself, you're always going to get bigger than 0 if U is not the 0 vector. And remember, when you dot 2 vectors, you get a real number. So that 0 is a real number. But I'm saying U is not equal to the 0 vector. And U dot U will equal the 0 vector precisely when U is 0. Letter B. The dot product commutes. U dot V is V dot U. Think about it. If you have 3, 2, 1, and you dot it with 4, 5, 3, when you multiply those two numbers, it's the same as if you were to dot these 2 vectors, 3, 2, 1, 4, 5, 3, excuse me. 3 times 4 is the same as 4 times 3. 2 times 5, even if you don't know what it is, it's the same as 5 times 2. And I mean, I know you know what 2 times 5 is, but if the numbers are less friendly. 1 times 3 is the same as 3 times 1. So yeah, of course it's going to be equal. Yes, it will be equal. Letter C. If you add two vectors, and then you want to dot it with a third vector, the dot kind of distributes. You can dot U and W plus, and then you can dot V and W. You can dot V and W. Letter D. If you scale the vector U by C, and then dot that with V, you could, if you choose, to scale the vector V with C and dot that with U. Or you can dot U and V first and then dot that with C. Now, when might you want to do this? Well, for example, when would you want to go from here to this one? When would you rather rewrite this like this? Answer, there's a natural reason why. If you have 7 times 1, 2, 3, C times U, and you want to dot that with V, which is 2 over 7, 3 over 7, and 5 over 7, it would be much easier to take the vector 1, 2, 3 and dot that with 7 times this vector, because 7 times that vector makes that new vector nice and clean. You get 1, 2, 3 dotted with, now 7, you multiply each of these entries by 7. And you just get the numerators, 2, 3, and 5. And this dot product is nice and easy to do. You don't want to get 7, 14, 21, and then multiply that vector, 7, 14, 21, with 2 over 7, 3 over 7, 5 over 7. That's just ridiculous. Let's suppose we did multiply that first vector by 7, and now we get 7, 14, 21. Okay, well, 7 times 2 over 7, that wasn't bad. That's 2, plus 14 times 2 over 7. Now you have to say 7 goes into 14 2 times 2 times 3 is 6, plus 21 times 5 over 7. 7 goes into 21 3 times. 3 times 5 is 15. So the answer is 23. I'd rather go 2 plus 6 plus 15. 2, 6, 15. 15, 21, 23. Okay, I don't want to deal with fractions. Okay, now, when would you like to go from the first expression in letter D to the last one? When would you like to factor out the constant? And the answer is, I suspect the answer is when the constant is not very nice. Like, if you have 2 7s times the vector U, 3, 4, 5. So that's C times U, and you want to dot it with 5, 6, 7. Now, if you did the if you did this first, you're going to have 6 over 7, 8 over 7, 10 over 7. And now you have to dot this with 5, 6, and 7. It's just very awkward. Okay, you have to multiply these, and now you get 30 over 7, and then this product is 48 over 7, and this product is 70 over 7, and you get 148 over 7, it looks like. And there was lots of fractions going on. There was lots of fractions. I'm not saying you're not going to have to deal with fractions. Okay, you want to deal with the fractions as little as possible. I think you should do the dot product first and then deal with the scalar multiplication of this number. So you have 2 over 7, and you want to multiply that by this dot product. So you have 2 over 7 times 15 plus 24 plus 35. That's 50 plus 24 is 74. So you get 2 over 7 times 74. 3 times 74 is 148 over 7. This was the only time I dealt with fractions. One time. Okay, one last thing. Why you would want to go from the first to the third. What if the absolute value of the scalar, and I don't care if it's positive or negative, but it's a very, very large number. It's a very large number. And I'm not going to do this because I'm not going to know the products. But if you have 132 times, okay, 4, 3, 2, and you want to dot this with 3, 1, 1. Now, if you multiply those, you get big numbers. 528 or 396 and 132. And then you'd have to multiply these numbers. Let's make these even bigger. By 344. Because 132 times 4 is large. And then you have to multiply that by 3. 132 times 3 is 396. You have to multiply it by 4. We can get around that. We can say, wait. We'll deal with the 132 at the end. Let's dot these two vectors and multiply the result by 132. You get 12 plus another 12, that's 24, plus 1 times 4 is 4, that's 26, right? 28. So now you just have to do 132 times 28, okay, and you work that out. That's just one big multiplication. The largest number I got was 12. And I got it from 3 times 4. I didn't multiply 132 by 4 and then multiply that large number, 528, by 3. That's going to give me 1584. 1,584. And that's if I didn't make a silly mistake in my head. You don't want to deal with big numbers. So letter D, that's my favorite one. Now, why would you ever use C the way it's written? That is, to go from the left to the right? I cannot really think of why. However, I can think of lots of reasons to go. Remember, equality goes both ways. What I'm just putting a box around is equal to what I just underlined. That is, you can go from the right to the left. Now, let's see what's going on with the right. You have to do two dot products, which each depending, and if you're in Rn, you have to do n multiplications. So multiplications, you have to do 2n. N from here and n from here. And additions, you would just have to do one addition. Now, if you did from the left, let's see how many multiplications you'd have to do. Well, you add these two vectors in Rn, you'll get a vector in Rn. You'll get a vector in Rn. And then you dot it with W, which is Rn. So you only have to do n multiplications. Instead of, so you don't have to do half as many multiplications. Now, here, since U and V are in Rn, you'd have to add the first two components together, the second two components, the third. You'd have to do n additions. There's no doubt about it. I would vote for this. Half as many multiplications and n additions. You know, in all, there were 2 plus 1 operations, and in the bottom, n plus n is 2n. The top has more, I don't know what I just called that number. More I think I said multiplications. The top one has 2n plus 1 computations, and the bottom has n and then another n. It has 2n computations. The top one has more computations, and they're harder. There's no doubt that I'd rather do n multiplications and n additions than n plus n multiplications. And then I have to do another addition? Yeah, I'd rather use this. Okay, so if you're given something like that, might as well do that, because letter C said equal. So, you know, it's one thing to know the theorems, or the properties, if you rather call them, but it's another thing to know when to use them. And that's the 4 parts of this theorem. Okay. Now we get into some fun stuff, in my opinion. I really enjoyed this lecture from my professor. He taught us, proved to us, the Cauchy-Schwarz inequality. This is a very neat theorem. It just came out of the blue. So I couldn't believe how brilliant some mathematicians were. And it wasn't my professor. He's not the one. He's not Cauchy nor Schwarz, but he certainly remembers it. The Cauchy-Schwarz, spell it somewhat right. S-C-H-W-A-R-Z. Inequality. Cauchy is very famous. To be honest, the only time I ever heard of Schwarz is in the Cauchy-Schwarz inequality. Okay. This theorem goes on to say the following. If U and V are vectors in Rn, then the following is true. Then U dot V, which is a real number, so when I put these bars around it, it means the absolute value of those real numbers. It is less than the length of U times the length of V. Okay. Now, the proof, let's suppose U is 0. Let U equal the 0 vector. Okay? Then U dot V is 0. Because the zero vector dotted with anything, if we're in R3 or R4, that's U, and you dotted with V, which may or may not be the zero vector. You know what? I won't even say what these values are. I'll call them A, B, C, and D. Well, certainly, 0 times A is 0 plus 0 times B is 0, 0 times C is 0, 0 times D is 0. I get 0. The zero vector dotted with any vector is the zero vector. In the last theorem, we said that the zero vector dotted with itself is a zero vector. We actually said something stronger. We said that if U dot U is equal to 0, that implies U is the zero vector. Think about why. Don't you see a lot of numbers being squared? And numbers are being squared. If U is U1, U2, up to U sub n, and I dot it with itself, U1, U2, up to U sub n. Well, when I multiply the first values, I get U1 squared, which is either 0 or above. If U1 is 0, you square it, you get 0. If U1 is positive or negative, when you square it, it becomes positive. Okay, plus U2 times U2, U2 squared. That's either 0 or positive. No in betweens. All the way up to UN plus UN squared. Now this is greater than or equal to 0. It's never negative. The dot product is never negative. I'm sorry, I didn't mean to say that. When you dot a vector with itself, it's never going to be negative. In fact, the only time it's going to equal 0, since the instant one of these are not 0, I'm sorry, the instant U1 or U2 or any of them are non-zero, when you square them, they'll be positive. Not 0, but positive. So the best, so either these values are positive or they're 0. And you can't take zeros and add positive numbers in once in a while and then get 0. That won't be true. The only way you'll get 0 is you're only allowed to add up zeros and positive numbers. The only way the sum is 0 is if all the numbers you added were 0. Okay, so that was just a side note. So if U is 0, U dot V is 0. Okay? Also, the length of U is 0. Because you square, remember, U is all zeros, however many. So the length of U, well, you square all those zeros and you add them up. You get 0 squared plus 0 squared up to 0 squared. You take the square root, you get 0. The length of the 0 vector is certainly 0. And then when you dot it with the length of V, it's also going to be 0. Okay? So, the length of U, which is 0, times the length of V, which may or may not be 0, is 0. And then yes, then U dot V, the absolute value, which is, the absolute value is 0 is 0, is certainly less than or equal to the right side, which is 0 as well. This is 0, and this is 0, and yes, 0 is less than or equal to 0. True or false? True. Some students tend to say, oh, equal. No, We're not asking you which is true. I'm asking, is the statement u is less than or equal to, I'm asking, is the following statement true? 0 is less than or equal to 0. The answer is yes. Because when it's or, less than or equal to, only one of the two have to be true. Okay, so we just isolated this special case. If vector u is 0, then this theorem holds. So what do we do next? We suppose something. We suppose u is not 0. Let's say now. Now suppose u is not the 0 vector. Okay, suppose u is not the 0 vector. So we consider, and this just came out of the blue, consider ru plus v, or r is some scalar. Okay? Consider that. Now again, when you dot the same vector with itself, it's going to get either positive or 0. That is, ru plus v dotted with itself has to be greater than or equal to 0. Okay? Well, let's dot it. We have the distributive law. Ru dotted with ru. Ru dotted with ru. Plus, let's say plus, ru dotted with v. Ru dotted with v. And then v dotted with ru. Plus v dotted with ru. Plus v dotted with v. Plus v dotted with v. Well, this is equal to ru dotted with ru. I contractor out the r's, get r squared times u dotted with u. Plus ru times v, that's r times u dot v. But this here is the same as r times v dot u. R is r, but v dot u is the same as u dot v. So we're adding two of them, plus v dot v. Okay. Now, let's look at what happens in a slightly different way, not much differently, but let's look what happens when you calculate, when you dot a vector with itself. When you do u dot u, u is u1, u2 up to un. You multiply the first components, and you get u squared, plus you multiply the second components, which are both u2, so you get u2 squared, all the way down to you multiply the last components by themselves. Un is the last component here, and u sub n is the last component there. You get un squared. Then you say, you know what? That looks very, very familiar. If I had a square root sign above that, that would be the length of u. I don't have a square root sign. Imagine for one moment I have a square root sign. Imagine I have the square root sign. If I square the left side, the square root sign leaves. And if I square the right side, it stays. That is, u dot u is nothing more than the length of u squared. Okay, so let's come here. I have r squared times u dot u. That is, I have r squared times the length of u squared, plus 2r times u dot v, plus v dot v. That's the length of v squared. That's the length of v squared. And like it says, it's greater than or equal to 0. Obviously, I need more space. So let me write this down again. I'm going to write down this stuff. We have r squared times the length of u squared plus 2r, 2 times u dot v times r, want the r at the end, plus the length of v squared. And this is bigger than or equal to the number 0. This looks like a quadratic. The right-hand side looks like a quadratic equation. If I call this A and I want to call that B, I want to think if I want to call the whole thing B. Okay, I want to call that B and that C. So basically, I have r squared times A plus 2br plus C. And I can always put the A in the front. That's a quadratic equation where A is equal to the length of u squared. Now remember, u is not 0. And the length of a vector can't be negative. And even if it could be, we're squaring it. So A is bigger than 0. And, I just want to change, it's going to matter. I just want to change the way I call these. I just want to call it big A, big B, and big C. So big A is the length of u squared, which is greater than 0, and he's just getting silly with notation. Little a is the length of b squared. Little b, for the quadratic equation, it's whatever r is being multiplied by. It's 2b, and little c is the length of b squared. I mean, I guess it might have just been easier. I'm sorry. Okay. So now, we know that A is positive. Okay? That means the quadratic opened up that way as opposed to that way. And we know this quadratic equation is either always bigger than 0 or it can equal 0. So we have two scenarios. That's the x-axis. It could come down and touch the x-axis in one place and one place only, or so it's either positive, it's positive here and here, and it's 0 right there. So it's either positive or 0, or it's always positive. It's always positive. It's one or the other. Okay, so we're going to look at each case separately. And remember, the quadratic formula is as follows. we have by the quadratic formula is that r is negative b plus or minus the square root of b squared minus 4ac all over twice a. Negative b. But b is 2b. It's 2 times that times r. Whatever r is being multiplied by, that's b. It's 2 times u dot b, which I'm calling 2b. Plus or minus. Now I square little b. I square 2b, I get 4b squared. Minus 4 times a, and I will call that big A. 4 times big A times big C. And this gets divided by 2 times A. Now, after memory algebra, negative 2b plus or minus 4b squared minus 4ac. What's under the discriminant? I can factor out a 4. So I get b squared minus ac. So the square root of this is the square root of 4 times the square root of the b squared minus ac. But the square root of 4 is 2 times the square root of b squared minus ac. And all of this gets divided by twice a. Now in the numerator, I can factor out a 2. I can even factor out a negative 2, but I won't. I'll factor out a 2. 2 times negative b gives me negative 2b. Plus or minus 2 times the square root of b squared minus 4ac. That gives me this. All divided by 2a. I did all that just to say the 2's cancel. Okay, so let's write it up one more time without the 2's there. Okay. So this is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Sorry, over a. The 2 cancel. Alright. Now, let's go back to our picture. Either we have 1 0 or we have no zeros. It never crosses the x-axis. Well, we have 1 0 when what's underneath the square root sign is 0. Because then we'll get negative b plus or minus the square root of 0 over a. And the square root of 0 is 0. So plus or minus 0 over a. And if you have negative b and you add 0, you get negative b. If you have negative b and you take away 0, you get negative b over a. That is one solution. Okay? So to get one solution, you want b squared minus 4ac to equal 0. That means equal for a moment or two, okay? To get no zero, to get no zeros, to get no roots, not to cross the x-axis, to get no real roots, that means what's underneath the square root sign must be a negative number. The square root of negative 7 is the same as the square root of negative 1 times the square root of 7. But the square root of negative 1 is I. You will get an I, an imaginary number. You will get an I. And so if this is an imaginary number, and you add it to b, or you take it away from b, which is a real number. Like if you have 3 and you add or subtract 7i, or the square root of 7i, that's an imaginary number. And when you divide it by a, it's still imaginary. So To get no roots, we want what's underneath the square root sign to be negative. To get one root, we want it to be 0. So b squared minus 4ac must be negative. So let us write that down. B squared minus, it was just minus AC, I'm sorry. Remember we factored out the 2. We had 4b squared minus 4ac, and this became 4 times b squared minus ac, and we had the square root. I can take the square root separately. This number was 2, and the 2 actually canceled out with the 2 in the bottom. So, and I hope I had that, I just wrote it down here wrong. So we want the discriminant that's underneath the square root sign. So used to writing that 4. We want it to be less than or equal to 0. We want it to be less than or equal to 0. Okay. Just play with some algebra a little bit, and everything will be okay. If I pass the negative AC on the left side to the right side, that is, if I add AC to both sides, I'll have that b squared is less than or equal to AC. B squared is less than or equal to AC. Taking square roots of both sides, b is less than or equal to the square root of AC. But what was b? B is u dot v. U dot v. And that's less than the square root of a. This is the same as the square root of a times the square root of c. The square root of a was the length of u squared, times c, the length of v squared. Okay, now I do have one little typo, and we need to talk about taking the square root. The square root of something squared is not the something. It is not. I mean, consider, if you take negative 5 and you square it, you get 25, and then you take the square root, you get 5. And you didn't get back negative 5. If you take 7 and you square it, that's 49. If you take the square root of 49, you get 7. You get back what you plugged in. Well, let's see. We plug in negative 5, we get back 5. We plug in 7, we plug in 7, we get back 7. You know what? That reminds me of the absolute value function. The absolute value of negative 5 is 5, and the absolute value of 7 is 7. This is not true. But the square root of x squared is equal to the absolute value of x is true. So when I take the square root of b squared, I get the absolute value of b. But b is u dot v. But that's not b. It's the absolute value of b. Okay. Now, the next line will give us the answer, but once again, we have to talk about absolute values. The length of v, I could say v, the length of u is not negative. The length of u is not negative. So if the base is not negative, and then you square it, and you take the square root, if that's not negative, you get back 3. if you know x is not negative, then the square root of x squared is the absolute value of x. But if x is not negative, the absolute value of x is x. Okay, that is the left side is u dot v. The right side is just the length of u. I don't have to take the absolute value because the length of a vector is not negative. Somebody asks you, how long is that line segment? You're really going to say, oh, it's negative 3 inches. Can't you tell just by looking at it? Okay. The length of v is not negative. The length of v is not negative. It might be 0. Okay? So the square root of the length of v squared is just the length of v. Now, possibly a moment ago, I said that u might be 0. Well, no, it can't be, because we ruled out the case where u was a 0 vector. The only way the length of u can be 0 is if u is a 0 vector. And it's not. Okay, well, bingo. This is exactly what we wanted to prove. And it involved a lot, and it was a nice theorem. And why do I show these things? The bottom line is, the more you can understand at the more advanced level, the more you'll understand at the lower level. So even if your test is going to be easy, if you can understand more than the easy stuff will be easier. If you only understand the easy stuff, then you can get tricked on a test. Easily be tricked, and that's the last thing you want to happen. You don't want a test to trick you. Okay. So now, let's look at a numerical example. So where we want to prove or verify, we want to verify that u dot v really is less than or equal to the length of u times the length of v. Now, if I let u equal to 304, and I let v equal to 512.0. Let's verify this. So, since I want u dot v, I'll put v right underneath. And why do I want u dot v? Because the formula tells me. So, u dot v is simply product of those two numbers, 15, plus the product of those two numbers, plus the product of those two numbers. It is 19. Okay? So, we want to write it down here. Fine, 19. The length of u is 3 squared plus 0 squared plus 4 squared. Now, you should know that there's a right triangle. You have to have some mathematical maturity. 3, 4, 5. 3 squared plus 4 squared equals 5 squared. Adding 0 won't do anything. So this is 5 squared, and the square root of 5 squared is 5, or 9 plus 16 is 25. The square root of 25 is 5. So is this less than 5 times the length of v? 5 squared plus 12 squared plus 0 squared. 5 squared is 25 plus 12 squared, that's 169. And the square root of 169 is 13. And I set you up again with 5 and 12. You should know the right triangle. 5, 12, 13. 5 squared plus 12 squared is equal to 13 squared. But that's what's underneath here. Hitting 0 doesn't do anything. So the square root will just be the square root of 13 squared, which is 13. And I wish I had one more line. I should say 19 is less than 65. 19 is less than, I wanted to say you have to know your 0 times table when I did 0 times 12. The next product is 4 times 0, which of course is 0. 4 times 0 is 0. The dot product is 15. And, yeah, 15 is definitely less than 65. So that's how you would verify the Cauchy-Schwarz inequality. Your teacher has every right to say, here's vector u and here's vector v. The teacher can give you this and nothing more except the instructions to verify Cauchy-Schwarz inequality. You're going to have to know Cauchy-Schwarz's inequality, folks. You're going to have to know it. Okay, there's no way around that. You're going to have to know the Cauchy-Schwarz inequality. And there's really nothing to really practice here because you're supposed to, we reviewed significantly how to compute dot products. We did it during learning matrix multiplication. We did it by multiplying matrices over and over. We did it earlier in this video. Finding the length of a video, finding the length of a vector is straightforward. You square each of the components of the vector and you add them up and you take the square root. It's just elementary school or high school mathematics. Just squaring numbers and adding them up and then putting a square root symbol over them. So your whole job is to know Cauchy-Schwarz inequality is nothing more than u dot v is less than or equal to the length of u times the length of v. Okay. Now, let's look at this from a very, very interesting point of view. U dot v, the absolute value of that, is less than or equal to the length of u times the length of v. Now, if I divide both sides by the length of u times the length of v, I get that the absolute value of u dot v over the length of u times the length of v is less than or equal to 1. Now, hand waving just a little bit. Let's suppose that neither u nor v is 0. Let's just suppose for a moment neither u nor v is 0. Okay? Then this is not 0 and this is not 0. But then it's positive. Each of them are positive. The length of a vector can be 0, but it can't be negative. Okay, so this is positive, which means that just because I feel like it, I can put absolute values by it. Like 7 is equal to the absolute value of 7. Anytime, if you want to write 2 plus 3, since they're both positive, you can write this. They're equal. The instant one of those numbers are negative, forget about it. 2 plus negative 7 is not equal to the absolute value of 2 plus the absolute value of negative 7. Alright, now we're going to stress on absolute values. Now, should have actually proven the next statement in your real analysis class, or advanced calculus. But it's nothing major. The absolute value of A divided by the absolute value of B is A over B, and then take the sign. Sorry, then ignore the sign. That is, take the absolute value. Okay. Now, you have negative 8 over negative 2. That's 4. You take the absolute value of the whole thing, you still get 4. If you take the absolute value of the top and then the absolute value of the bottom, the number you get is never going to deviate from 4. The sign might deviate. Okay? The sign might deviate. But this division might just differ by a sign from this division. In other words, the absolute value of negative 30 divided by the absolute value of 5. That's 30 over 5. That may not be the same as that. They'll just differ by signs. The left side is always positive. To make the right side positive, take the absolute value of the whole thing. Okay, this mess is less than or equal to 1 because it set it up there. Now, I'm taking the absolute value of the top, and I'm taking the absolute value of the bottom. That means I can take the absolute value of the whole mess. I can take the absolute value of the whole mess. It's u dot v over the length of u times the length of v, absolute value of the whole thing. What I just wrote down is equal to this. And it's less than or equal to 1. That means it's between plus and minus 1. That means that u dot v divided by the length of u times the length of v, it's between plus and minus 1. After all, if you ignore the signs of numbers between negative 1 and 1, you get numbers less than 1. You get numbers between 0 and 1. If the absolute value of x is less than 4, that means x is in between negative 4 and 4. Okay, and this, I didn't mean to put 1 or plus 1 or minus 1. In fact, I just meant to put 1. Well, what function can we think of that's always between negative 1 and 1? I can think of 2. The sine function, the sine of x, the sine of theta, or the cosine function. Now, I've never considered it could have been the sine function until just this second when I said it. Which is why instructors learn when they teach. But I can't really think of why they chose to put the cosine. But nonetheless, they called this the cosine of the angle. They said the cosine of theta is equal to u dot v over the length of u times the length of v. And the theta is the angle between u and v. What does that mean? Well, very simple. You have the vector v, you have the vector u. That theta is the angle between u and v. So they just chose to call that the cosine of theta, where theta is the angle between u and v. And it lives up to the fact that it's between -1 and +1. So now, and this is for any dimension, R2, R22, R13, doesn't matter. The cosine of the angle between any two vectors is the dot product of the two vectors divided by the length of the two vectors. Okay. Now, earlier, I said, not much earlier, I said, you know what, let's just hand wave a little bit when I said the length of u, and I can divide by the length of u times the length of v. Well, what if the length of u is 0? What if the length of u is 0? Or the length of v is 0? Oh, I do want to say one last thing. Should have comma here and say that theta is in between 0 and pi. So why not bigger than pi? Very, very simple reason. If this is u and this is v, there's really two angles I can have. I can talk about two angles. I can talk about that angle, or I can talk about that angle. We always talk about the smaller one, okay? If it's almost 180 degrees, we don't say it's 182, but rather we say the angle between vector v and vector u is 178. And I'm not going to talk about when u or v is 0. At least not yet. Okay, so we'll give you a numerical problem. That is, I'm going to give you two vectors and ask you to find the angle between them. If u is 1, 0, 1, 0, and vector v is 0, 1, 1, 0, find the angle in between. So first we do u dot v. 1 times 0 is 0. 0 times 1 is 0. That 0 times that 0 is 0. But 1 times 1 is 1. So u dot v is 1. Okay? The length of v, I meant to write u, but I wrote v. Don't bother squaring the zeros. You want to find 0 squared plus 1 squared plus 1 squared plus 0 squared is 2. So we have to take the square root. The length of v is 2. The length of u, well, u has the same numbers, 2 zeros and 2 ones. Well, you think if I write them in different orders, they won't add up to the same? No, it's going to add up to 2, the square root of 2. So this tells me that the length of u times the length of v is the square root of 2 times the square root of 2, which is 2. Okay? So the cosine of theta is equal to u dot v divided by the product of the lengths. U dot v is 1. The product of the lengths of u and the lengths of v is 2. The cosine of theta is 1 over 2. Okay, so let's look at this. So we have 1 over 2. And that other side is going to be the square root of 3. The side opposite, so let's see. Oh, that was silly. I can still do it, but let's do it the way most people do it. Cosine of this angle is adjacent over hypotenuse, 1 over 2. And this is the square root of 3. Opposite 1 is 30, and opposite the square root of 3 is my 60-degree angle. 60 degrees. So this tells me that theta is 60 degrees or 180 degrees divided by 3. And if you don't see a degree symbol, but it's obviously an angle, it means radians. Pi over 3 radians. You don't have to write the word radians. So theta is 60 degrees or pi over 3 radians. The angle between these two vectors in R4, I can tell you what it is. It's 60 degrees. Okay, and why can you do it in R4? The answer is, when you take the dot product, you always get a real number. And when you take the lengths of two vectors and multiply them together, you get a real number. Get a real number. And we know, since u dot v is less than the absolute value, is less than the absolute value of u, the length of u times the length of v, then I know that when you put this on the bottom, you get less than 1. That is, the absolute value of this is less than 1. That means it's between negative 1 and 1, just like cosine is. You'll always get an answer. You'll always get an answer. Which is pretty nice. It's always good to get an answer. Okay, let's look at this definition. Two non-zero vectors, u and v and Rn, are said to be orthogonal if u dot v equals 0. Two non-zero vectors, u and v, and Rn, are said to be orthogonal. Said to be orthogonal if the dot product of the two vectors are 0. What if one of the vectors is 0? If one of the two vectors is in fact the 0 vector, then we will say that the two vectors are orthogonal. Really need the space. Orthogonal. If one vector, if only one of the vectors, if exactly one of the two vectors is a 0 vector, then we'll still say the two vectors are orthogonal. That means perpendicular. Okay, now what is the angle of perpendicular lines? 90 degrees. So basically, when you have the following, when you have the cosine of theta between u and v, it is possible that u is the zero vector. If u is the zero vector, you have problems because the top will be 0 and the length of u is 0 times the length of v, which will be 0. It is telling us if the cosine that's not what I want to say. Okay, excuse me. So, just ignore what I said. U is not the zero vector. U is not the zero vector. I'm sorry. Okay, none of these are the zero vectors. But if they're orthogonal, then u dot v would be 0. And if neither of them are the zero vector, the product of their lengths will not be 0. And 0 divided by not 0 is 0. And the cosine of what angle between 0 and 180 is 0? 90 degrees. Just look at the cosine graph, only up to pi. The only place where it crosses 0 is at pi over 2, which is 90 degrees. Okay. So what it's saying is if you have a zero vector and any other vector that isn't 0, we're going to say that those two angles are orthogonal, and if the angle between them is 90 degrees. Why? Because somebody felt like doing that. Mr. Mathematics woke up one morning and said, you know what? The angle between the zero vector and a non-zero vector is 90 degrees. Well, what if the vectors are parallel? What if the vectors are parallel? Two non-zero vectors are parallel if, let me think, if u dot v is equal to the length of u times the length of v. Well, exactly what does this mean? Well, if the vectors are non-zero, neither of these are 0, and hence the product is not 0. So that means that the length of u dot v divided by something that it equals, you divide two non-zero things that are equal, you get 1. Okay, you get 1. But that means that u dot v without the absolute value bars divided by the length of u times the length of v is equal to, well, let's talk about this for a moment. If this is 10, then u dot v can be positive 10 or negative 10. Because when I take the absolute value, I still get 10. Okay, and if this is 10 and this is 10, then I get 1, positive 1. But if this is 10, when I divide them, that is this. But if the bottom is 10 and the top is negative 10, then I get negative 1. Okay, so I get plus or minus 1. Alright, so let me erase this. Now, if the part that remains, let me erase a little bit more and put back something. this equality holds with the absolute values there, then that means that this quantity is plus or minus 1. It means that quantity is plus or minus 1. But what I have circled in the bottom, that's just the cosine of theta. Cosine of theta is 1 or it's negative 1. Well, let's look at the cosine graph. Only up to pi. Well, it's 1 at 0 degrees and it's 1 at 180 degrees. Okay, so if you have a vector like this, and the other vector, the angle between the two vectors is 0, then the other vector must be right on top of it. Maybe it's longer, maybe not. But in any case, they're parallel, and the angle is 0, so the cosine of angle is plus 1. The cosine of 0 is plus 1. Now, what if they're 180 degrees apart? That means one angle goes that way, and the other angle goes the complete opposite way. Their angle is 180. The vectors are parallel, but in opposite directions. When the cosine of theta is plus 1, the angles are parallel, and they go in the same direction. When the cosine of theta is negative 1, they're parallel, but they go in opposite directions. Okay, let's formally write that up. And think about it. You have to think about it for an hour. Well, guess what? You need to think about it for an hour. Whatever you do, stop thinking about it for 10 minutes. You know, I learned that early on in linear algebra, is that you cannot move on until you understand what you were supposed to know prior. Okay, so two non-zero vectors are said to be parallel. So we're kind of defining when two vectors are parallel. If the absolute value of u dot v, the absolute value of u dot v is equal to the absolute value of u times the absolute value of v. Okay. They are in the same direction if u dot v is equal to the length of u times the length of v. Okay, they are in opposite directions if negative u dot v is the length of u times the length of v. And you should understand that, and anytime you forget it, you can come up with it. It's not a major thing. The angle between two vectors are 180 degrees. Then the cosine of 180 is negative 1. That is, you don't want the top and bottom to be equal. Remember, the cosine of theta is the division of two quantities. And if the angle is 180 degrees, And the cosine of 180 is negative 1. That is, if this is negative 1, then u dot v does not equal to, well, let me just write it down. When does a fraction equal negative 1? And the answer is when the bottom is 8 and the top is negative 8. Also, if the bottom is negative 7 and the top is positive 7. The thing is, doesn't matter, but we'll never have the product of the lengths of two vectors be negative. But a fraction is 1 is when the top and bottom differ by signs. So the top equals the bottom, no. They differ by a sign. And the cosine of 0 is 1. That is, this is 1. Oh, I know when a fraction equals 1. That's exactly when the top and the bottom are equal. You just know when a fraction equals 1. When the top and the bottom are equal. Okay. Time for numerical example. How about we let u be the vector 1, 0, 0, 1, vector v equal to 0, 1, 1, 0, and vector w is 4, 0, 0, 4. And there are commas when needed. If you compute u dot v, 1 times 0 is 0, 0 times 1 is 0, 0 times 1 is 0, and 1 times 0 is 0. So u dot v is 0. Now, same thing with v dot w. 0 times 4 is 0, 1 times 0 is 0, 1 times 0 is 0, and 0 times 4 is 0. You add up all those zeros, you get 0. Well, this implies that u and v are orthogonal. v dot w equals 0. That implies v and w are orthogonal. They're both orthogonal. But what about u and w? What about u and w? Now, you really should see that w is just 4 times u. If you multiply each of these entries by 4, you get w. It's called magic. But you didn't notice that wouldn't matter that much. U dot w. U is this vector. I dot it plus w, which is this vector. You get 4 plus 0 plus 4 plus 0, or 8. And the length of u is 1 squared plus 0 squared plus 0 squared plus 1 squared. 1 squared is 1, 1. 0 squared is 0. You add them up, you get 2. The square root of 2. The length of v, you square 4, you get 16. You square another 4, you get 16. Square root. Now, since I know the square root of 16, I'm not going to add the 16s. I'm going to say that it's 16 times 2. The square root of 16 times the square root of 2. And I know the square root of 16. I do not know the square root of 2. Okay. The length of u times the length of v. It's the length of u times the length of v. The square root of 2 times the square root of 2 is 2. times 4 is 8. Now, u dot v over the length of u, that's the u, trust me, times the length of v is, well, u dot v, let's see where it is. Ah, shucks. The vector was w. U and w, sorry. The length of w is 4 square root of 2. Okay. Just a silly typo, folks. The length of u times the length of w is 8. Alright. So now, u dot w divided by the length of u times the length of w. Well, u dot w is, just go to the right, is 8. And the length of u times the length of w is also 8. We get 1. Plus or minus 1 means parallels. So u and w are parallel. And since we got 1 in the same direction as opposed to in opposite directions, are parallel and in the same direction. Okay. The next thing we're going to talk about is a consequence of the Cauchy-Schwarz inequalities. I'm going to talk about that. And this corollary, this consequence, has its own name. It's called the triangle inequality. A consequence of the Cauchy-Schwarz inequality is the triangle inequality. State the theorem. It's actually a theorem. It's not even going to be called a corollary. And the name of it is triangle inequality. And it says the following. If u and v are in Rn, then the length of u plus v is less than the length of u plus the length of v. Now, before we prove this, I want to motivate it in R2. If this is u and this is v, this third side has to be smaller. Okay, and let me draw it more appropriately. If I start here and I go that way, that's u. And then from u, if I come up here, that's v. So from here to here, since I went from tail to head, and then from tail to head, that resultant vector is u plus v. But we know that the third side side of a triangle can't be bigger than the other two sides. That is, the length of u plus the length of v must be, or the length of the sum cannot be bigger than the sum of the individual lengths. That's exactly what the theorem states. Okay, actually, when would you really get equality? When would you really get equality? The answer is as follows. Suppose vector u looks the following way. One moment, please. Suppose vector u starts here and it goes that way. That's u. And vector v picks up right where vector u stops. And vector v goes that way. Well, what's the sum? Well, the sum is the vector that goes from the beginning to the end. So, how long is this vector? Well, it's the length. The sum of the individual lengths will be the length of u plus the length of v. But the sum vector, like I said, it starts from here and it finishes there. It's that straight angle, that straight line. So that's the length of u plus v, and they are equal. Because the sum of the parts is the whole. This piece plus this piece, how long? Well, I broke it up here. This piece plus this piece, assuming they lie in a straight line. How long is it? The length of the whole thing. So only when the angles between the two vectors are 180 degrees and they go in the same direction will you have equality. But you'll never have more than this. The length of u plus v cannot be more than the length of u plus the length of v in R2. And the triangle inequality is saying that it's true in any dimension. It's true in any dimension. I suspect that the motivation to prove this triangle inequality was that we knew that it was true in R2. Okay. So the proof goes like follows. Consider the length of u plus v squared. Okay? That is, I'm starting with not the left side, but the square of the left side. Okay? But remember, the length of any vector, say w squared, that's just w dot w. This vector, w is u plus v. This is just u plus v dotted with u plus v. So you get u dot u plus u dot v plus v dot u plus v dot v. That's the v. V dot v. V dot v. So we have this. The length of u plus the length of v is equal to u dot u. That's the length of u squared plus u dot v plus v dot u. Well, v dot u is u dot v. So u dot v plus u dot v is 2 u dot v. plus the length, plus v dot v, which is the length of v squared. Okay. Now, what is the Cauchy-Schwarz inequality? Okay, that's the one we have to know. What is the Cauchy-Schwarz inequality? It says that u dot v in absolute values is less than or equal to the length of u times the length of v. Now, this is bigger than this. I need a little bit more space to write that. The length of u dot v, the absolute value, is less than the length of u times the length of v. But now, either the absolute value of u dot v is equal to u dot v, or u dot v is less than. In other words, if this is 7, this can be 7 and they're equal, or this can be negative 7. Okay, so what I want to say is that u dot v is less than this. Okay, so instead of u dot v, I'm going to put something less. I'm going to put 2 times the length of u times the length of v. And the other 2 terms I'm not touching. This term I'm not touching. The length of v squared. Okay. And now we have it. The left side, the bottom line, is a perfect square. The bottom line is a perfect square. Okay, so I'm just rewriting this, and I'm going to write it again. It's less than, this is a perfect square. It is the length of u plus the length of v squared. Okay. Now, this is positive, and that's positive. Okay, so when I take square roots of both sides, which I'm about to do, I don't have to worry about absolute values. You know, if a is less than b and they're positive, if that, then the square root of a is less than the square root of b. I'm looking for a number that when I multiply it by itself gives me a. That's what that value is. I'm looking for a number that when you, over here, I'm looking for a number that when you multiply it by itself gives me b. Well, if b is bigger than a, then this is going to be bigger than that. Alright, so therefore, the length of u plus v, taking the square root of both sides, is less than the length of u plus the length of v. That's neat. This is true in any dimension. Okay, that's really neat stuff. Doesn't matter what dimension you're in. The length of u plus v is less than or equal to the length of u plus the length of v. In R2 and R3 and R25, doesn't matter what dimension we're in, less than or equal to. Okay, let us prove this. If u is 1, 2, 3, and v is 2, 2, negative 3. So I want to show that the length of u plus v is less than the length of u plus the length of v. So first let me find out what u plus v is. U plus v is equal to 1 plus 2, 3, 2 plus 2, 4, 3 plus negative 3, 0. Okay, and I set it up to be 3, 4, and 0. So the length of u plus v is 5. 3 squared plus 4 squared, 9 plus 16 is 25, plus 0 squared is still 25, square root is 5. Okay, so the left side is 5. What is the length of u? It's 1 squared plus 2 squared plus 3 squared. 9 plus 1 is 10, plus 4 is 14. It is the square root of 14. And the length of v is 2 squared plus another 2 squared plus 3 squared, or negative 3 squared if you insist. 4 plus 4 is 8, plus 9 is 17. Okay. Let's see if we can figure this out without a calculator. The square root of 14, well, the first number below 14 I know the square root of is 9. It gives me 3. And the first number above 14 that I know the square root of is 16, which is 4. So the square root of 14 is between 3 and 4. Now, 17. The first number below 17 that I know the square root of is 16, which is 4. Okay? Now, I actually don't care about the right side. I didn't have to do the right side of either the square root of 14 or the square root of 17. But for completeness, I'll do it. The first number above 17 that I know the square root of is 25. This tells me, adding the left sides, adding the middle, adding the right side, it tells me that this number, the square root of 14 plus the square root of 17, is between 7 and 9. In fact, I don't care about 9. This is bigger than 7. Okay, so we know that the length of u plus v is 5. And yes, that is less than the length of u plus the length of v. Because this is at least 7. It's bigger than 7, not even equal to. This is bigger than 7. And you better believe 5 is less than all numbers that are bigger than 7. Even if they're no bigger than 9, 5 is less than them. So you just work it out. The numbers get in the way. If you don't, you say, well, I need to do a lot of these examples. Just watch the, or I meant to say, the instructor on the video, need to do a lot of these examples. In this case, I'll say no. If you didn't get it yet, not a big deal. Reverse the tape and watch it again. The numbers don't have any real play in this. It's the technique. Add u and v together. Find the length of u and v. Find the length of u. Find the length of v. Add them together. See if one is really less than the other. Okay. last thing I want to talk about before we do this theoretical exercises is the following. What is a unit vector? A unit vector called the vector u. A unit vector in Rn is a vector of length 1. Is a vector of length 1 unit. 1 foot, 1 meter, 1 whatever. Let x be a non-zero vector. Let it be a non-zero vector. Then vector u, if we define vector u to be x divided by the length of x, then u equals that is a unit vector, but it's more than that. It's a unit vector in the same direction as x itself. Why? Because x divided by the length of x is 1 over the length of x times x. And 1 is a positive number, and we said x is non-zero, so the length of x is positive. If the top is positive and the bottom is positive, this is positive. If you multiply the vector x by a positive scalar, it's going to be in the same direction. Like if this is x and 1 over the length of x is more than 1, well then that new vector will just be longer. If 1 over the length of x is less than 1, remember this was x, well then fine, that would be the new vector u. If the length of x is 1, well, 1 over 1 is 1. 1 times the vector x is the vector x. It'll be the same exact vector. It's when this scalar is negative when the vector changes direction. I'm going to put down a vector, and we're going to find a unit vector in the same direction as the original vector. By just dividing the vector by its length. So if x is the vector 1, 0, 1, 0, 1, we want to find a unit vector in the same direction as x. So how you do that is you just compute that. So I need to know the length of x. Again, squaring zeros don't do anything. You have 1 squared plus 1 squared plus 1 squared. That's 3. The square root of 3. I'm done. X divided by the length of x. You take each value of x, there's 5 of them, and you divide it by square root of 3. 1 over square root of 3, 0 over square root of 3 is 0. 1 over the square root of 3, 0 over the square root of 3, and 1 over the square root of 3. And there it is. That's let's call it u. That vector u is a unit vector, and it's in the same direction as x. Now, let's just see that we're correct. That is a unit vector. One over the square root of, so the length of u is 1 over square root of 3 squared plus 0 squared plus 1 over the square root of 3 squared plus 0 squared plus 1 over the square root of 3 squared. Square root. Well, 1 squared is 1. Square root of 3 squared is 3. 0 squared is 0. 1/3. 0. 1/3. A third plus a third plus a third is 3/3 or 1. Plus 0 is still 1. And the square root of 1 is 1. Now, that's one way of doing it. Another way of doing it is to just outright prove it. That is, prove it in general. Prove that x over the length of x is in fact a unit vector. Maybe it was just true for this one example. Maybe it's always true. You never know. You never know this stuff, folks. Pretty sure, well, maybe not in Rn, but I'll just state it. The length of a constant times a vector u is the length of vector u times the absolute value of the constant. Because if that constant is negative, if this number is 7, but c is negative 2, then you get negative 14, which makes no sense. This is a vector. How can the length of a vector be negative? Oh, maybe I'll take the absolute value of negative 2, and I'll get positive 2. Okay, so what is the length of x over the length of x? Well, first we can think of it like this way. It's 1 over the length of x, a scalar, times the vector x. And using the theorem I just stated, it's the absolute value of that scalar. This is a scalar times the length of x. But 1 is positive, and the length of x is positive. You can only convert a non-zero vector into a unit vector. So both of these are positive, which means I don't need the absolute value bars. That cancels out to 1. 1 times 1 is 1. Oh yeah, it's always 1. Provided that vector x, this is only if x is not the zero vector. Assume x is not the zero vector. And the length of x over the length of x is honestly 1. So now you don't have to go and show that the length of this is 1. Unless you think, the 1, the 0, the 1, the 0, and the 1 are all correct. And there's an understood square root of 3 here. So the only way this is not a unit vector is if we have the wrong length of x. Theoretical exercise. Under the theoretical exercises, we'll actually prove this theorem I just stated, that the length of c times x is the absolute value of c times the length of vector x. So, suppose the following. Suppose u is orthogonal to v and w. To v and w. We want to show that U is orthogonal to any linear combination of U and W. Show that U is orthogonal to any vector in the form R times V plus S times W, where R and S are scalars. So proof. Two vectors are orthogonal if their dot product is 0. Okay, so I want to show that U dot RV plus SW is 0. Well, this is U times this vector, U times RV, plus U dot SW. But we talked about this before. I can put the R in the scalar in front. It's R times U dot V, plus the scalar can come in front. It's S times U dot W. But U dot V is 0. R times 0 is 0. Plus S times U dot V is 0. Because U and W are orthogonal. And U and V are orthogonal. U is orthogonal to V, and U is orthogonal to W. And 0 plus 0 is 0. So yes, therefore, U is orthogonal. Let that symbol mean orthogonal. Is orthogonal to R, V, plus S, W. Okay. Let's prove one of the properties in that theorem that I stated. U dot V plus W is U dot V plus U dot W. We want to show that U dot V plus W is U dot V plus U dot W. Let U equal to U1, U2 up to UN. V equals to V1, V2 up to V sub n. And W is equal to W1, W2 up to Wn. So we'll compute the left-hand side. U dot V plus W. Well, U is U1, U2 up to U sub n. I want to dot this with V plus W. V plus W. That's V1 plus W1, V2 plus W2, all the way down to Vn plus Wn. And if I dot this, that means I multiply those. U1 times V1 plus W1, plus multiply those. U2 times V2 plus W2, all the way down to I multiply UN with Vn plus Wn. UN times V sub n plus W sub n. But how I add is up to me. I want to add I want to multiply u1 and v1 and then add u2 with v2 all the way down to, I'm going to add un plus vn. Un times vn. Plus, now I'm going to add on the ones I didn't add on yet. u1 w1, u1 w1 plus u2 w2 all the way down to un wn. un wn. But this first bracket is u dot v. This is u dot v. u1 times v1, u1 times v1, u2 plus u2 times v2, all the way down to un times vn. Plus, because it does say plus, and this second bracket is u dot w. u1 w1 plus u2 w2, u1 w1, u2 w2, all the way down to un wn. That's what I wanted to show. Theorem is done. Or proof. Proof is done. Okay. Remember, the square root of a squared is the absolute value of a. Let u be a vector in Rn, and C is any scalar. Then the length of C times U is the absolute value C times the length of U. We want to prove this. C times U is C times U1, U2 up to UN, which is CU1, CU2 up to CUN. Okay, so now the length of CU is the length of this vector, which is CU1 squared plus CU2 squared all the way up to CUN all squared. Square root of that. Now please remember, if you have a product, AB, this being squared, you have A squared, B squared. So this is C squared, U1 squared. This squared is C squared, U2 squared. All the way down to this squared, which is C squared, U2 squared. Square root. Hope it's a little bit obvious that I can factor out C from what's underneath the square root sign. Sorry, I can factor out C squared. So underneath the square root sign, I have C squared times U1 squared plus U2 squared all the way up to UN squared. Let's clean that up. U1 squared plus U2 squared all the way up to U sub n squared. Now, we have a rule that if not both of these are negative, the square root, if A and B are not both negative, if A and B are not both negative, one can be negative or none. And the square root of AB is the square root of A times the square root of B. Well, this here can't be negative. Oh, what just happened? Let me just put that back. Sorry for the delay. Okay. What's in the second bracket is not negative, and c squared is not negative, so I get the square root of c squared times the square root of u1 squared plus u2 squared all the way up to u sub n squared. And here's the results. The square root of c squared is the absolute value of c times the square root of this mess is, by definition, the length of u. So I got just what I wanted, and this video for n vectors is complete.